Here's one of the two main numerical analysis methods we're going to cover in Math 9. This one is called the Bisect Method. The other one is called Newton's method. And it's based on the following theorem. And this theorem says if I have a continuous function and I have some input where the function is negative, and I have some other input where the value is positive, where the output is positive, then there exists a root somewhere between x negative and x positive. And so the proof, well, let me just say what the name of the other theorem is to use to prove this. This is by the intermediate value theorem. And what does the intermediate value theorem say? It says if you have a continuous function and you have any two outputs, then every output or every number between those two outputs also occurs. So here I'm applying that to the very specific output, 0. And what's the visual proof of this? So say here is my x positive. And you might think, oh, I'm screwing up because I put x positive on as a negative number. But x positive, what that means is that the output is supposed to be positive. So for example, let's switch to another color. For example, if the graph of f of x is up here, then f of x positive is positive, which is what we want. And let's say it looks something like this. The graph y equals f of x. And then, well, I don't have many choices for x negative. Okay, my only choices for x negative are somewhere here. So let's say here at this minimum value, we have an x negative. And what does continuous mean? Well, it's sort of difficult to define precisely, but intuitively it's not difficult. This function is continuous because there aren't any jumps or breaks in the graph. Okay, and why is this theorem true? Well, it's saying if I start above the x-axis and end below the x-axis, or vice versa, start below and end above, and I'm not allowed to have any jumps in the graph, then at some point it exactly crosses the x-axis. And so this value here, this would be the z that we're looking for. Okay, I mean, there's another possible value of z here on the right, but the intermediate value theorem or the bisect method aren't going to find this second value of z. They're only going to find this one that's in between. And so that's all theory. What's the actual algorithm? So here's the algorithm on which, or here's the algorithm of the bisect method. So we're assuming we're starting with x negative and x positive. Then where does the bisection happen? xb for bisect. Bisect means cut in half. So I want to find some value that's midway between these. And how do you find a point midway between two other points? Just take their average. So I can take x negative plus x positive divided by 2. And I'm not going to try to write this in MATLAB code. We'll see that in one of the other videos. Instead, what I want to give is what's the pseudo code for the algorithm. So we find what's the input that's midway between x positive and x negative. And here's one way to think about it. Lots of times I ignore the case of what happens if x bisect is the exact 0, but let's check it here. So if f of x bisect is exactly 0, okay, even though I'm doing pseudocode, I'll write it with 2 equal signs just to remind you. That's how we do true-false equality. Okay, then we want to output x bisect. And the reason I usually skip this kind of step is because we never expect to find a 0 exactly. We just expect to find it up to some error threshold. So this is a little unrealistic, thinking that the output will be exactly 0. So here's the the more important part of the bisect method. So if f of x bisect is less than 0, then we're going to set, hey, this is not part of MATLAB language, it's just pseudocode. We're going to set x negative equal to x bisect. And if f of x bisect is positive, okay, then that means this could have been a new x positive value. So I'm going to set x positive equal to x bisect. And then this is a recursive algorithm. We keep doing this again and again until we're within a certain amount of accuracy. So I just say repeat here. And let me show you what happens over on the graph. So x bisect, let's say, I can't really tell where it would be. Say this is my new x bisect, halfway between x positive and x negative. So should this be x positive or should this be x negative? Should definitely be x positive because the graph is above the x-axis here. So this is my new x positive. Okay, and now I repeat. So what does that mean to repeat? I divide this smaller interval in half. So the reason this is a good algorithm is because we keep getting closer and closer to the 0, or we at least keep getting a smaller and smaller interval that contains the 0. So this would be my new x bisect. And should this replace x positive or x negative? Should replace x positive again. Okay, because the graph is above the x-axis here. So you just keep repeating, and there are a few different ways to decide when to stop, or a few options for deciding when to stop. Either I can stop when this interval gets really small, really narrow, or I can stop when I plug in say the x bisect and get a really small output. Okay, so either I know that I have a really narrow interval that contains the 0, or I know that f of x bisect is very close to 0. Those are my two options, and neither of them is really better than the other. It's just good to recognize that they're not equivalent, and you do have those two different options.